Okay, so this is the second video explaining 4 more problems on the extra practice solutions. And again, feel free to just fast forward to the question you have, look at all the answers. But again, sometimes it's nice if you are stuck to listen to the explanation and kind of see the process that I'm going through or hear the process I'm going through. So our first one is just a u substitution in the exponent. And so x squared would be my u. And so I'll let u equal x squared, and its du is equal to 2x dx, off by a factor of 1/2. So, I like this problem because it's not a hard u substitution, but I like this problem because it's a good reminder of how to integrate when it's not just e to the x. In this case, it's like it will be 3 to the u. So I have my antiderivative of 1/2 3 to the u du. Let's change our bounds. So 0 squared is still 0, but now 2 squared becomes 4. And now I don't have to think about x's anymore. Well, our antiderivative of 3 to the u, remember, is itself, but then we've got to divide by the natural log of 3. And now we're going to evaluate this from 0 to 4, our new bounds. Now, this natural log of 3 is at the same degree or level as the 1/2. So it's like 1 over 2 natural log of 3. And then times 3 to the u when evaluated from 0 to 4. So then 1 over 2 natural log of 3. And then I could say, okay, well, that's 3 to the 4th, which is 81, minus 3 to the 0, which is 1. And 81 minus 1 is 80. So now I have 1 over 2 natural log of 3 times 80, and then 2 goes in 80 40 times. So I could get 40 over natural log of 3. Now, some of you maybe were pretty clever, and before we did the actual evaluation, you saw this step right here and said, guess what? I know that 2 could come as an exponent of 3, and it's the same thing as natural log of 9. So some of you may have gotten an answer that doesn't look like mine, but it's equivalent. Maybe you have 80 divided by the natural log of 9. Those are numerically the same value, so that's fine. Next, I love it because, I know it's going to be completing the square. Hopefully you're at a point you can recognize why we have to complete the square. Again, this is quadratic and this is a constant that's 2 degrees. So that's a good indication it's inverse tangent. Without the square root there, at least it's an inverse trig function. And then without the square root, I know it's inverse tangent. So let's go ahead and complete the square before we get too far. X squared plus 8x plus 16 plus 97 minus 16. So that's x plus 4 quantity squared plus 81. So that's what I'm going to integrate. So I'm going to integrate 3 divided by x plus 4 quantity squared plus 81. And then that's from 5 to 14. Okay, so let's take a look. Let's let u be x plus 4. So the derivative is just dx. We have 3 of them. And then 81, that's nice. Doesn't always have to be a perfect square, but in this case, my a value is equal to 9. So we'll rewrite. Now my integral becomes, let's see, a 3. And then it's 1 over u squared plus 9 squared. Let's check the bounds. 5 plus 4 becomes 9. And then 14 plus 4 becomes 18. Now this is inverse tangent. Don't forget we have this 3 here. And then it's arc. Oh, but don't forget also, it's 1 over a. So 1 over 9. And then arc tangent of u over 9. No plus c because we're going from 9 to 18. That's 1/3 arc tangent. And then let's see, 18 over 9 is 2 minus, use bracket there, arc tangent of 1. So, I'm hoping you recognize arctan of 1 is pi fourths. if you left it like this and it was a free response type of question, open-ended type of question, you would still get full credit. But if this, let's say, were multiple choice, I'm trying to erase this, not very well. If it was multiple choice, it would be in its most simplified, or expect you to know that that's pi fourths, and I'm giving up on that straight mark. So 1/3 arc tangent of 2 minus 1/3 of pi fourths, or pi twelfths. Excellent. All right, next problem. We're going to do completing the square again, and it's our first time we've done completing the square which potentially, or you'll see in a moment, it'll be arcsine. And I know it's arcsine because it's a square root. And again, looking at the degree, I have a 4th degree here. This is more than 1 away, so I know it can't just be a simple u substitution. So I'm going to recognize and think about rewriting this in terms of like a u first. That might make completing the square a bit easier. So this thing here, let's let u be 2x squared, because that thing squared would be 4x the 4th. So my du then is 4x dx, which is okay. I have an x up there. So 1/4 du is equal to x dx. And the other thing too, this 8x squared, that's going to be equivalent to 4 u's. So I can rewrite this as 1/4, and then it's going to be 1 over the square root of 9 plus 4 of the u's minus u squared. When you complete the square for inverse sine, what you want to do is factor out the negative, because we want it to be like a squared minus u squared. So I'm going to do a little bit of a rearrangement here. And so I took out the negative, so that's u squared minus the 4u. And then half of 4 is 2, and 2 squared is 4. And that's really, though, a negative 4. So then I have to add 4 to balance that out. And that 4 and the 9 will come together as a 13. So now I have the antiderivative of 1/4, and then it's 1 over the square root of 13 minus u minus 2 squared. So now at least I'm in that characteristic u and a of inverse sine. Now, you may be inclined, and it's perfectly fine, to do another u substitution, like a w substitution. But also realize, though, that since the coefficient of this u here is 1, its derivative will still be 1. So you don't necessarily have to do it in that particular case. Or when you do it, you'll realize that, oh, it's going to be the same, same antiderivative. So I'm gonna know that this is 1/4. Now there's no 1 over a, and then it's just arc sine of u over a, or u minus 2 over a, which is the square root of 13. And this might be our first time we have such kind of like an awkward the a, and that's okay. Not a perfect square. That's okay. We just need to go back and say what was u. So 1/4 arc sine of 2x squared minus 2, all divided by root 13 plus c. Okay, excellent. Okay, and then one more example. This is another inverse trig function, or u substitution in disguise, where I'm going to let my u actually be the root x right there. We'll let u be that root x, because 1 over root x sort of will represent its derivative. Well, close. Remember, the square root's derivative is 1 over 2 root x dx. We just have 1 over root x dx, so we're going to need a 2 du equals 1 over root x dx. And my bounds can change as well. So let me go back to purple. Oh, I like orange. Why not? So I've got 2. And then let's see, the square root of 4 becomes a 2. Square root of 9 becomes a 3. Now I know this right here would be a 2u, but then x is technically the square root of x squared. So I can think of this as 1 over u squared plus 2u plus 1. Now, initially I thought maybe, this might be inverse tangent, but it's already a perfect square. So I can square that So 2 to 3, not square that, I'm sorry, factor that. So it's 2. That's 1 over u plus 1 squared du. So this is not going to be an inverse tangent. It's not even going to be an arc function. Sorry, it's not inverse tangent. It's not going to be a log function because I'm going to do another little substitution. Let's say w equals u plus 1. So dw, any fans of Arthur out there? dw equals just du. So what's going to end up happening here is that you're just going to be integrating 1 over w squared dw. And that's the same thing as integrating w to the negative 2. Well, that's just a power rule. So it's not even natural log, right? Oops, sorry. So then that's just w to the negative 1 over negative 1. And what was w? Oh, it was u plus 1. So this becomes negative 1 over u plus 1, which is nice. Oh, yeah, no, I guess I have this 2 out here. I don't know why I left that 2 out there. No idea. So I get negative 2 over u plus 1 when evaluated from 2 to 3. So when I put a 3 in there, I get negative 2 over 3 plus 1 is 4 minus negative 2 over 2 plus 1 is 3. So I have negative 1/2 plus 2/3. Well, negative 1/2 is the same thing as negative 3/6. And 2/3 is the same thing as 4/6. So I get positive 1/6. Now, how maybe you're just still wondering too why it's not inverse tangent. Like, how could you tell that this shouldn't be inverse tangent? Well, if you think about this for a second, here's why. Okay, so this doesn't work. So not equal, in case you're fast forwarding. If you try to complete the square, so u squared plus 2u, you put the 1 here. Oh, so I add 1, but then I got to subtract 1. So then I get 1 over u plus 1 squared plus really 0 squared. So there's the structure of arctangent. I haven't changed the problem yet, but here's how I know that it can't be arctangent's antiderivative, because right off the bat, it's 1 over a, which is not possible. And then you think like arctangent of u over a, again, can't divide by 0. So that's why that doesn't work. So so make sure that like if you're watching this, you realize that that's not a solution. And that's how I knew that it wouldn't be arctangent. Okay, very nice. So again, if you're just logging in to see the answers, there we have 1/6. And then let's see, here's another answer here. So feel free to go back and look through the video to find that solution. 1/3 arctangent of 2 minus pi/12, and either 80 over natural log of 9 or 40 over natural log of 3. And I feel like I've said this a lot too. Remember, the goal, the point, the idea is that you get good at recognizing the different antiderivatives, strategies, and processes.